Okay, that's gone. Okay, let's see. As far as things that why printers have been down, but you haven't been able to for weeks. So as far as the exam goes, there's only two off the week 3 assignment that I really like. I like number 29. That's a short one that you should be able to work out pretty quick. Yeah, that's a good one. For exams, since kinematics are from last semester, you can still use them because they're easy to follow, but I'll only do those in homeworks. I'm not putting those on exams or whatnot. The other one that I like is number 73. You're gonna have to, because that, like, you have to have something Gauss's law. Yep, 29 and 73, and then number 4 from homework 1.
Homework 1?
Yep.
Yeah.
Number 4. Yep. Let's see here. Wait, why is that on there? Why is that one on there twice? Okay, that one's a lot. This one, number 3.
Oh,
So we're gonna have two that are very similar. So like this one, number 3 here is on electric forces. And then yep. If you can do number 3, you should be able to do this one. It's a superposition theorem. That one.
we get that lab done.
I don't know. You should be able to do this. It's superposition. Well, because once you figure out the fields, the electric force is just Q times E. So you don't have to redo the whole thing. You can just use Q times E. Well, you'll get the same answer. It'll just take longer. So the key to the one I just showed you in this one is knowing which way your vectors point. So for forces, you have to remember repulsive versus attractive. For fields, you have to draw the vectors away from positive and towards negative. So as long as you get your vectors in the right positions. Yep. Yeah. What were you doing? Number 73. And number 29. Okay. Okay. And then, so that's this, you remember that's the second half of the exam. You remember the first half is concepts. So like I would make sure you know things like it's like, you remember last semester when I asked you like what is the mathematical expression for Newton's second law? Well, it's like you could like what is the mathematical expression for Coulomb's law? Yeah, so you'd need to know that because that's a definition. No. Nope. I'm gonna try to see if you know the difference between 1/r and 1/r squared laws. Which one is the 1/r law? Which one is the 1/r squared? Law. Yep. Yep. Things like remember that little bit we did on like charging by inductance, charging by conductance. No, they would. The first half will be. The second half, you'll have to show me all your work, but it should be something you've already done. Okay. Everyone knows that one. Everyone knows that one. Which way a positive angle rotates? See, it would be helpful if people were actually here, but since you and like these two are the only ones who'll know, might do that. I have to find a way to work lizard into the exam.
What's your shirt said that?
Oh, this is just a bunch of physics laws. That's a Schrodinger equation. That's a solution for the wave function. There's Planck's law. It's kind of a short turnaround, don't you think? I don't think Etsy can do that.
No, I'll make.
You could probably get it off Etsy for, you could probably get a screen printed t-shirt off Etsy for, $200, but don't get it from Temu. I don't want to see what that ends up as.
We have terrible to go.
Yeah, was it what you actually ordered? Okay. If you ever want to be terrified, go to St. Louis and go to the IKEA store. You have to have road signs in there just to get out. Oh no, it's terrifying. You pick out what you want, and then they send you into the catacombs to find it for yourself. Yeah. What? Okay. So we're still talking about potential energy. So electric potential energy. So let's make sure we're keeping our terms straight. We're going to have potential energy and we're going to have potential. Those are two different things here. Okay. So your potential energy, you can still think of as an uphill thing. So it's going to be in opposite directions for positive and negative charges, because as you bring a charge closer to its like charge, potential energy increases. That's your uphill direction. You have to force it to go that way. You have to do work to move it towards its like charge. But here, we say that we have 2-point charges. They're separated by 15 meters. What is the electric potential energy? Okay, so let's do the potential energy. I'm just going to put. Come on, are you serious? I don't need this shit right now.
figure out.
Uh-huh. I don't know what it's doing. I don't know what it's doing. How is it there? It was making the iPad scroll, but not writing. And sometimes if you tap these, they act weird. So we'll put Q there and little Q there. A lot of the time, yeah, in problems like this, we just want to be you could have called it Q1 and Q2. So most of the time, big Q will be total charge, especially if we're dealing with like Coulomb's law. The textbook decided to do this like this so that it could instead of Q1, Q2. I'm not a fan of it, but I like to try to keep consistent with the textbook so you don't see something in here and then something in the book and go, what's this? Okay. The potential energy yep. So it's QQ over R. And so when you work this out, you're going to get about 0.018 Newton meters, which is also the what? The Newton meter is the what? Nope. Coulomb is charge. What are we calculating here? Potential energy. The Newton meter is the what? Joules. Well, but you have to know if you're doing a calculation, if all the units that are in the calculation are work, like, do they work? Do they have units like this in biology? Okay. You're probably dealing a lot with like kilocalories and stuff like that. Kilojoules, joule, okay. Now, part B. Let's see. Does little q move towards or away from big Q? Does little q move towards or away from big Q? It moves away. They're both positive. It's repulsive. Let's see. How does the motion of little q affect the electric potential energy? It will. Are we losing that energy? Yeah. So what was potential energy as little q moves away, it's gaining velocity. So the potential energy becomes kinetic energy. Mm-hmm. Velocity is 0. Father, is that what it says? Yes. Oh. I don't know. Lately, autocorrect has been trying to do it's been trying to choose a lot of stuff for me. I'm like, I don't, and the autocorrect lately has been making things less grammatically accurate. I don't know what's going on. I mean, pretty much. Well, I was making like a quiz question today and I put choice E, like E inside of parentheses, because it was like selection E. And when I did parenthesis, autocorrect went, did you mean the euro symbol? Did you want the euro symbol? I put the euro symbol. Why would I want the euro symbol? Yeah. What I miss is Clippy. I miss Clippy. Would pop up at the worst times, like you're depressed one day, uh, you're writing something about how depressed you are, Clippy pops up. I noticed that you're writing about your depression. Would you like me to help you make this grammatically accurate today? No.
The first and stupid.
Yeah. So Clippy's like, I know you're depressed, but you really screwed this up. Let me help you.
Learn this now.
So how do we find the potential energy for an array of charges? So the first thing you have to do is figure out where these charges are. You have Q1, Q2, Q3. They're all positive. Well, there's one there. One there. Hard to get things one straight above the other when your parallax is off. Okay, so there's Q1, Q2, Q3, and then we have 3 meters. There's not a Q4. 4 meters. Now, if you have 3, 4, 5 triangles, you can do that. Otherwise, I'd like to see you use the Pythagorean theorem just to make sure you've proven that a side is what it is. But I'll only accept that for 3, 4, 5. Otherwise, I want to see you calculate it. Okay, so our generalized theorem for potential energy it's not an E.
Somebody monster. I wrote on my test, but I just feel like
Yeah, I get things where people go,
mine's like a back 3. I get too lazy to draw that. Try my best to draw it, but sometimes my brain just physically cannot comprehend. But is the I is that just
No, those are indices. It's a shorthand for. Same thing.
But do you have
No, those are indices. I could make it N and M if that'd make it easier to. Yeah. Because this is saying it could be like Q1, like, and more accurately. Right. Because you can't have a force with a charge interacting with itself. I just tried to shorthand it a little bit. Because I just want you to know, I just want you to realize that you're going to do this, but you're just going to add them all together for all the different charges. So what this is going to become. So the first potential energy is the Q1, Q2 over R12. So those are all of our interactions. I don't think anyone would make this mistake, but let's find out. Does this seem like this takes care of all of the interactions between the particles? I have 1, 2, 1, 3, and 2, 3. Do I need to take account? Do I need to take account of like 3, 2, 3, 1, 2, 1? Yeah, so those are the exact same thing. We want to make sure, like, always be careful you're not double counting. Oh, I don't want to put all these numbers in. So I don't want to write the numbers down. Just remember that when you do this, your Q1 because you see they're microcoulombs. And then what Q3 is 3.0. And so then you put all your numbers in there, you should end up with a potential energy, a total potential energy. Yeah, I just don't want to write out all those numbers. You just have to remember when you're looking at the problem and you see like the microcoulomb, you're going to want to put 10 to the negative 6 on there, turn it into coulombs. Again, if we were doing a problem that said, so someone again remind me, what's that? Yep, 10 to the negative 9. So you'll see that quite a bit too. Lizard? Okay, so that's electric potential energy. Now I need to talk about electric potential. Okay. So this is the difference. So your potential, or V, it, mhm, is going to be potential energy divided by Q, so divided by one of the charges. Okay, so again, if we think of this time, of course, I'm using big Q because in potential itself, you're looking at the potential due to only one charge, or the total charge of the system. And then your SI units for potential are going to be volts. Joules per Coulomb could also be Newton meters per Coulomb. And then if you really wanted like the base SI units, what do newtons break down into? I know. Kilograms? Yep, meters per second squared. So if you ever have to break down to the base SI units, remember that newtons are the kilogram meters per second squared. So it'd be kilograms meters squared per second squared. That's the joule. Okay. And just like everything else, potential follows the superposition principle. You okay? It's just it's just like Q1, Q2. You're adding them all together out to however many Qs you have. But you won't usually. But now I feel like I want to put one on the exam that has 10 of them. You max out at 3. Stay away from molecules.
But that's when you this my IQ score, she said, put 3 on me. So it's just called me dumb.
Yeah, I was trying to figure out where you were going with that. Liam brings our Q down to 1. I was
-2.
I should you know what? We could do the potential for an entire molecule. But well, you'd be writing that for I don't think you'd finish in a day. That's tens of thousands of electrons. So you'd have to write this something like 20, 30,000 times. Now, there's another way you could do that if you had 30,000 electrons. You could either write this out 30,000 times, or what could you do? Huh? Not ratio.
30,000.
2 dot 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 dot. No, it's 3,000.
No, you're making it way too hard.
Times it by how much? 2 to the as many what? I'm a genius.
You could do it once and multiply by 30,000. Now, the problem is if the electrons are all at a different R, and then you can't do it. Yeah. I feel like you guys are wanting a lesson in density functional theory. That is not even remotely what I said. No. It's funny, and I will laugh later. But there are certain things like when the group over here says, I can't do that, I'm just a girl, like there are things I don't touch because they're minefields. Like the day I put up the equation for impulse. No, that's the no impulse. Last semester, I'm not touching that one. Oh, yeah. I said it last semester. I'll say it again. Y'all need Jesus. Fine. I shouldn't do this. I shouldn't do this, but I want you to look it up. Uh, um, popular singer used to be on, no, she used to be on the Disney Channel. No,
What's
crap. There was a, she's in the movie Wicked. Yes. She re, so she recently interviewed Adam Sandler, another old guy who's not up on TikTok memes. And he said in this movie we did this thing about 6 or 7 times, and you could see her face. She was going, like, watch it. She was about to lose it because he had no idea what he said. And Ariana Grande was going, oh God, no. I don't know what it means, but then how do you use it in speech if it doesn't mean anything? We don't do gang signs in here. Now, now let's say we have another group of charges. We have a 4 microcoulomb, a 2 microcoulomb, and a -3 microcoulomb. Let's see. Find the electric potential at a point B and the work done by the electric field if a charge Q moves from point A to B. So let's draw this out, see where everything is. I'm glad you guys at least still know who Adam Sandler is. That's so. Have you seen Little Nicky? You have to watch Little Nicky. Blazing Saddles, yes. Yeah, I can't repeat half that movie in public. No, no. Okay, so let's start placing these charges. If you really want to freak out, watch the movie E.T. and then remember that the little girl in there is Drew Barrymore. No, he was awesome.
I was about to tell you not to give single movie recommendations.
You guys chose to watch Holy Grail. You entered into that genre, and then Life of Brian was too much for you. Holy Grail, all Monty Python is strange. Okay, so point B is going to be about right there. Point A is going to be about right there. And so then we can start there's Q3, Q1, Q2. Okay, so let's see. A is at 0, 1. So I know that's a distance of 1 centimeter. Let's see. Q3 is at 2.2. So let's see then. If Q1 is at 0.3 and A is at 0.1, that means this intersection here is 2 centimeters. Okay. Okay, so the first thing we want is the potential energy at point B. Okay, so the first thing that I'm going to do is I'm going to do a line here. That is going to be R3B. That's hard to read. That's R3B. Then we're going to have R2B. Close enough. That's another thing about today's world that bugs me. Is I said a quote one time, and somebody knew what it was, and I go, "Oh, you know Shakespeare," and they go, "Who's Shakespeare? That's Bad Bunny." And I was like, "I quit. I quit. I quit. I freaking quit. I can't." No. I'm sad that I know who he is. No. I don't watch SNL because it stopped being funny like 30 years ago. When I watch something funny, I want to watch something funny. I don't want to get on there and have a bunch of people who think that they're intellectual giants go, "You want to know what I think about politics?" No, I don't want to know what anyone thinks about politics. I just do the joke, man.
Just do the job.
So no, I don't watch SNL. I do like Key and Peele.
What's this now?
No. Okay. Now, how do we start finding these distances? It's R1B. Okay, so how do you think we start finding these distances? Triangles. So we're going to do one. Oh, so we can make a triangle there. Now I know that that one side is 2 centimeters. Do I know the base of the triangle? Yes, because point B is, yeah, it's at 2 centimeters. So that's 2 centimeters. So R1B, that is going to be so then R1B comes out to be about 2.83 centimeters. Okay, so we have that one. What about, so R3B is pretty straightforward. What is it? Yep. Because again, we can look and see that Q3 is at 2.2, and then point B is at 2.1. And so we know the distance between B and Q3 has to be 1 centimeter. So you remember how to read these coordinates, right? Oh, okay. Because after you haven't done it for a while, some people go, "Wait a minute, what are those?" Now, what about finding R2B? Another triangle. The A. Oh, okay. Trying to think here. You actually, well, that'd be a roundabout way to do it. Yep. You can do it that way, but yes, it would be harder. Which side? Yep. So both of them are 1 centimeter. So that means your R2B this is going to give us 1.41 centimeters. So now we have all the distances that we need. Okay, now the potential at point B. And KE is a big number, so I don't want to write it a lot. And now you plug in your numbers. You're going to have to change all your charges to coulombs. They're all in microcoulombs right now. Okay, so this the Q1 is 4.0. 10 to the negative 6 coulombs. So at point B, you're going to get a potential okay. Your potential at point B comes out to be a negative number. Can you begin to tell me what that means physically? It doesn't have a direction. It is. So let's think about that. Think about this in the same way as current. When we end up looking at current, we're going to draw the current around a circuit, but the electrons in the circuit move the opposite direction of the current. So then if that's true, the current is measuring the movement of what? Not electrons. If current's the opposite direction as the electron movement, so positive charge. So let's look at this in terms of positive charge. If we put a positive charge in here, so what this is telling you is for a positive Q, the potential energy would be lower so you're gonna have a lower potential energy at point B. A lot of things we do in electrodynamics is judged from the view of the positive charge. Now, let's look at part B. Part B says, oh, I guess there wasn't a part B, but we found the potential and work done by the electric field if a charge of Q moves from A to B. So negative Q is going to move that way. Oh, did I even do that? Yeah, I did. Okay. So we already did this equation. So the work of the field, what is work equal? So let's just use potential energy. If we're doing the work of the field, that equals how do we put potential energy in there? Remember, your work is a positive kinetic energy, or now our potential energy is going to be negative Q delta V. So we can use that. So we've run into something you may not be happy about. Not really. But look what we have here. And subtract it off of what? We have to find potential at A. Do what? Yeah, so I'm gonna draw out the graph and we'll finish it next time. I wondered if anyone would notice that. It's like, well, we have VB. Oh crap, we need VA. Do what? Well, we didn't need to. Let's see, there, there, B, A. So what, the first one we have to find? This one's easy. It's right there. To find that one. To find that one. So we'll finish this up next time. We'll plug it in. So those are the ones we have to find now.